just like we did for n space, we can define the angle between vectors in a real inner product space using the Cauchy-Schwarz inequality. So we have the absolute value of the inner product between two vectors is less than or equal to the product of the norm of vector A and the norm of vector B. So in n space, the inner product is the dot product. And if we divide through by the product of the norms of vector A and B, we get 1 on the right hand side, and we don't change the inequality. And then removing the absolute value, we get an additional inequality. Now there is a unique angle theta such that the cosine of theta is equal to the inner product between vectors A and B on the product of their norms where the angle theta is between 0 and pi. So if you plot cosine theta between 0 and pi, you'll see that cosine of theta is unique. And given that's the case, we can take the inverse of both sides. So that gives theta is the arc cosine of this quantity. And this is defined as the angle between two vectors A and B in a real inner product space. We can also extend length and distance from n space to a general real inner product space. So if we have three vectors, A, B, and C, in a real inner product space, and S is any real scalar, then the triangle inequality for vectors states that the norm of the sum of two vectors is always less than or equal to the sum of the norms of each individual vector. And we saw this geometrically in 2 space, where the length of the sum of the two vectors is always less than or equal to the sum of their individual lengths. And the triangle inequality for distances states that the distance between two vectors, so you can think of this as the distance between vectors A and B being the distance between points P and R. And that's always less than or equal to the distance between vector A and C plus the distance between C and B. So this distance can be thought of as the distance between points P and Q, and this distance from point Q to point R. So let's look at an example. If we have the inner product space P2, which is a set of all polynomials with a degree less than or equal to 2, and we have the inner product between two polynomials defined as the integral of the product of their components with respect to x, and we integrate from -1 to 1. And suppose we have two polynomials, being P with a component of x, and Q has a component of x squared. And recall that the norm of a vector is the square root of the inner product of the vector with itself. So therefore the norm of p plus q is equal to the inner product between p plus q and itself. So what we have is x plus x squared by x plus x squared, and we're integrating over x, and then we take the square root to get the norm. So if you expand this out, you'd get x squared plus x cubed plus x cubed plus x to the 4. So therefore, this integral evaluates to x cubed on 3 plus 2x to the 4 on 4, or x to the 4 on 2, plus x to the 5 on 5. Evaluated at minus 1 and 1. And then we take the square root of this. So what we'd get is 1/3 plus a half plus a fifth minus a third minus a half minus a fifth. So the half cancels, and we'd get 2/3 plus 2/5. So what we'd get is 10 plus 6, which is 16 on 15. And we take the square root, so that gives 4 on root 15. And similarly, if we evaluate the norm of p, that's equal to the integral from minus 1 to 1, and the polynomial p has a component of x, so we'd have x multiplied by x integrated over x, and to get the norm we square root this. So this gives x cubed on 3 evaluated from minus 1 to 1, and we take this to the power of a half. So we get 1/3 minus a third, which is 2/3, and we take the square root. And recall our vector q had a component of x squared, so the inner product gives the integral of x squared by x squared with respect to x, and taking the square root gives the norm. So this gives x to the 5 on 5 evaluated at minus 1 and 1. So 1/5 minus a fifth gives 2/5. So we get the square root of 2/5. So therefore, you can verify that the norm of p plus q is less than or equal to the norm of p plus the norm of q by the triangle inequality. If we have two vectors in a real inner product space, these vectors are orthogonal if the inner product between these vectors is 0. So for the real vector space of n tuples, the inner product may be the dot product. And for example, if we have the vector space of polynomials with a degree less than or equal to 4, equipped with the inner product of two vectors, which is defined as the integral from minus 2 to 2 of the product of the components integrated with respect to x. So suppose P has a component x squared and Q has a component of x cubed. So the inner product between these two vectors is defined using this integral. So P of x is x squared and Q of x is x cubed, and we're integrating from -2 to 2 with respect to x. So by the power rule of integration, we get x to the 6 on 6 evaluated from -2 to 2. So we get 2 to the 6 on 6 minus -2 to the 6 on 6. So a negative number to an even exponent gives a positive result. So we get 2 to the 6 minus 2 to the 6 on 6, which is 0. So therefore P and Q are orthogonal. If S is a subspace of the inner product space V, then the set of all vectors in V that are orthogonal to every vector in S is called the orthogonal complement of S. So we denote this as S with a perpendicular superscript. So for example, recall that we had a matrix that we reduced to row echelon form, and therefore the row vectors in this reduced form form a basis for the row space of this matrix. So we have R1 with the following components: R2 with the following components, and the third basis vector is 0, 0, 1, 5 on 2. So any vector in the row space of this matrix can be expressed as a linear combination of these basis vectors. And from this, you can obtain a solution to the homogeneous system, which is the null space of this matrix A. And you'll find this basis vector for the null space of A. So therefore the null space of A has a dimension of 1, and the row space of A has a dimension of 3, being the number of basis vectors in each case. So recall that the row space and null space are orthogonal complements of each other. And we can show this by taking the dot product between this basis vector in the null space and these basis vectors in the row space. And you'll be able to verify that the dot product of this basis vector with all of these basis vectors, which is the same as the inner product in this case, is equal to 0. So effectively all the vectors in the row space of A are orthogonal to all the vectors in the null space of A.